May I present now to you this year's George A. Ola Award recipient for his work in hydrocarbon and petroleum chemistry, Professor Alex Bell of the University of California at Berkeley and Lawrence Berkeley National Lab. He has actually his own award symposium, and we're very grateful that he has been shuttling over here to help us celebrate Bert's award. He has many awards to his name, among those the Paul Emmett, the Robert Birchall Lectureship, and the Michael Boudard Award, all of the North American Catalysis Society. And he is a member of the National Academy of Engineering and American Academy of Arts and Sciences. Several hundred publications to his name, and he has been the editor of numerous journals and serves currently as the editor on the editorial board of Journal of Catalysis, Catalysis Letters, and Topics in Catalysis. The title of his presentation is Utilization of Synthesis Gas for the Production of Fuels and Chemicals. Please help me welcome Professor Bell.
So thank you for the kind introduction. That's more than I had expected. It's also a pleasure to run over here literally to participate in this wonderful symposium honoring Bert. And he's the recipient of the Distinguished Researcher Award from the division here. I've known Bert for probably over 40 years, first meeting him at a Gordon conference back in the 70s. And interacted a lot, particularly in the area of Fischer-Tropsch synthesis, where he has done an enormous amount of work using isotopic tracers and other techniques. So it's a great pleasure to be here and to contribute to the symposium in his honor, and to see Bert in his usual position sitting behind the video camera. Because as many of you know, another of Bert's constant activities is to video speakers at various conferences, North American Catalysis Society conferences, ACS, AICHE, and keep this for the historical record. So thank you for doing that, Bert. I've chosen as the theme for my presentation the utilization of synthesis gas for the production of fuels and chemicals, because this is not only a timely issue, but one that relates a great deal to what Bert has been doing throughout his career. So I'll go right to the first slide here and remind you that there is now renewed interest in Fischer-Tropsch synthesis, because it affords us a way forward to take virtually any kind of carbon source, be it biomass, natural gas, or coal, depending on your locale, depending on the kind of resources you have available in your country, convert this into synthesis gas, and then pass this over a catalyst that turns that into a spectrum of hydrocarbons ranging from methane to wax. And I identify various classes here. Methane is actually not a desired product, and one would like to minimize that, to keep it so maybe below 5%, 3% even if you can, of the total carbon consumption. Light petroleum gas is the C2 through C4, maybe up to C5 fraction. Gasoline is the next one, C5 through C11. Diesel, C11 through maybe C22. And beyond that one has waxes, but this is not a waste product because you can hydrocrack the wax and bring these products back into the diesel and gasoline range. And so the challenges for people who are working in Fischer-Tropsch synthesis is to keep the methane yield down, because this is a waste of carbon, increase the yield of products in the C5 plus range, because they can be reshuffled and put into diesel and gasoline, and then to find clever ways of using the LPG, principally the alkene fraction, to feed that back into the gasoline and diesel pools. So I'm going to talk to you today about two areas of effort that we have been undertaking here. One has been to identify how you could promote cobalt on silica, cobalt being a very typical Fischer-Tropsch catalyst, so that it produces less methane and more C5 plus material. And the promoter that we have found very effective is manganese oxide, particularly in very low quantities. And then I'm going to tell you a little bit about what we can do with the C2 through C4 alkenes, which are too light to blend into the liquid products, but can be brought back into the liquid range by increasing carbon numbers by combining them in various ways. So let's proceed to the first case. After reading the literature and considering various possible promoters, we settled on manganese oxide. And in tests that we did at 1 atmosphere, we found that the rate of CO consumption would increase nearly a factor of 2, not a very large amount, but still it's an increase, upon addition of manganese. And the amount of manganese that you'd have to add for the optimum is about 0.125 manganese per cobalt, which for the large cobalt particles we're looking at starts to approximate, on a stoichiometric basis, 1 milliliter. Beyond that, the activity falls off, and if you really go very high, you can drive the activity down to 0. And the changes in activity, which we see, are consistent with the observation of the kinetics, which at 1 atmosphere are largely dependent on the product of the partial pressure of hydrogen and CO, and a prefactor there that carries information about the rate of CO activation, the equilibrium constants for hydrogen and CO absorption. And so what we can say is that by one means or another, the value of A increases upon addition of manganese. What's more important, though, is the product distribution changes. And if you look at the blue bars, that's with manganese, the red bars without, you see there's a substantial drop in the methane make, substantial increase in the C5 plus make. And if you look over here specifically at C5 plus as a function of manganese addition, you see you go from roughly 30% to nearly 50%, about a 20% jump with a very small amount of manganese addition. Now the story gets more interesting if you go to high pressure, which is where Fischer-Tropsch would normally be practiced. So we're going now to 10 bar and looking at the effects of conversion. We see now that the rate is essentially independent of the conversion of CO for either cobalt without manganese or cobalt with manganese, although in this case, rather than seeing an increase, there's a drop. This is again at a manganese to cobalt ratio of 0.125, which we found to be optimal at 1 atmosphere. And that too is consistent with the kinetics, although now they're different, because in this extreme of high pressure, now this denominator term becomes large relative to 1, and the rate expression boils down to the ratio of hydrogen to CO partial pressures rather than the product, which was the case at 1 atmosphere. And since the consumption ratio of hydrogen to CO is very much like the feed ratio, 2 to 1, there's no change in the rate of CO consumption here. And what the decrease over here suggests to us is that by adding manganese, we've increased the equilibrium constant for CO absorption, which drives down then the rate, but only slightly. But what is more interesting is to look at the product distribution, which now we see has considerably less methane when manganese is added. And even more interestingly, as we drive the CO conversion to higher and higher values, we will now fall below the 5% mark, which is kind of the target, at about 50% conversion. And we can drive it even below that as you get to making principally liquid products. Concurrently, we see the same thing happening in the C2 through C4 fractions, although the rate here is higher in the case of manganese. And you can see now that the C5 fraction is higher, and we drive that fraction up as we increase the conversion. And we understand why these things are happening, because under these circumstances of high pressure, these light alkenes are being actually consumed and re-entering the chain growth process, driving down the monomer concentration and therefore the tendency to make methane, and driving up the concentration of making higher molecular weight products. So with these empirical observations of manganese, it's interesting to ask, so where is the manganese and how does it affect the cobalt? Well, this is turning out to be a more challenging question to address. If you look at bright field images of the unpromoted and promoted cobalt, particle size is roughly the same, but you can't differentiate where the manganese is. And this is because the Z values, atomic numbers for cobalt and manganese are relatively similar. If you go to dark field imaging, you can see the particles once again. And by doing EDAX, looking at the X-rays emitted from the electrons, you can see now maps of cobalt and manganese. There's one for oxygen, but this I won't talk about. And if you overlay the maps, the green and the red, you get areas of yellow over here, showing you the coexistence of manganese and cobalt. Now, it doesn't tell you exactly where the manganese is, in part because you're looking at a two-dimensional representation of a three-dimensional object, and also because in the microscope that we use, the resolution is only 2 nanometers by 2 nanometers. So each pixel, if you could see them, is 2 nanometers by 2 nanometers. Our particles are on average 8 nanometers, so this is not, this is only a large fraction of a particle diameter. And so what we're currently doing is moving to more sensitive microscopes that have a resolution of half a nanometer. And then we will eventually, having proven what we can learn with that type of instrument, go to the National Center for Electron Microscopy where we can get atomic resolution. So that's work in progress. But so far, what this suggests is that we have at least 2 cartoon-type visions. The blue here being the cobalt particles, so roughly 8 nanometers across. And there's good evidence that about 70% of the manganese lies on top of the cobalt, because that's the two-dimensional correlation. And the rest may be in little patches, some of which is sitting on the support and only partly contacting the cobalt. And what we will do as we go to higher resolution microscopes is resolve which of these 2 pictures is more correct, or whether there's a balance and what the balance is. So let me move on now to the next theme, which is what do you do with these light C2 through C4 materials that are produced. And here's an illustration from the catalyst that I was just describing of the C2 through C4 paraffins. You notice that there's a slight decrease as you go to higher CO conversion, but not much. And the C2 through C4 olefins are falling off, and this is because they're being consumed by reincorporation into the chain growth process. But we're going to ask, what could you do with these materials to bring them back into the liquid pool? And of course, you could always dehydrogenate the paraffins and put them into the alkene pool as well. And so what we're going to do is look at 3 scenarios. The upper one is very similar to the talk that preceded mine. It involves oligomerization of the light alkenes to make heavier materials, albeit it'll be with a nickel catalyst rather than with an acid catalyst. The second option is to take the alkenes, add CO and hydrogen to it, do hydroformylation, so you add a CHO unit to the alkene. And then you can hydrogenate that aldehyde to make an alcohol. And I'll show you specifically that we can take propene to butanol in one reactor with 2 catalysts in a very effective fashion. A third alternative would be to do hydroformylation and then aldol condensation. But you could do also aldol condensation if you were making the aldehydes by dehydrogenating, say, alcohols that had come from biomass. So this is an alternative strategy. And then you can hydrogenate products that look like this to make either branched alcohols or take off the OH group by hydrogenolysis and make a branched alkane. So oligomerization first of the 3. The process is straightforward to describe. You start, for example, with propene, absorb it, add a second propene, make the C6 intermediate, which you can resorb as hexene, and then you can continue to make nonene and the higher oligomers. And what the literature teaches us is that nickel catalysts, isolated nickel catalysts, are very good. But most of this literature is patent literature, and there's not much science to understand what the nickel is doing, how it's working, and how you keep the material active. So we've pursued this by looking at what is regarded as one of the better catalysts, nickel exchange sodium X. And we've prepared this by taking sodium X, commercial sodium X, with a silicon to aluminum ratio of 1.2, and doing aqueous exchange with nickel nitrate, and then doing thorough characterization by XSAPs, Zanes, temperature-programmed reduction, and from that concluding that the nickel cations are all distributed as nickel cations. There are no nickel-nickel particles, no nickel oxide. And at low loadings, what we learned is that the nickel cations sit in the windows of the hexagonal cages. They're not in the supercage here. And that has consequences because nickel sitting here isn't really accessible to the propene or other alkenes to do oligomerization. And so as a consequence of that, what we see is a very interesting pattern of nothing, no activity initially, rising activity, hitting a peak, then declining, but if you wait very, very long, this begins to line out, and then you can go for hours with an active catalyst. And what we've discovered is that as you add more and more nickel, the situation gets worse. You go up faster, but then you fall off, and you go to a lower level. And after some thought, what this teaches us is that you need to keep the nickel loading low enough so that there's on average only one nickel cation per supercage. And the reason for that, you'll see here on the next slide, is that initially you have to extract the nickel cations from inside the hexagonal cages to the windows of these cubooctahedrons, which are the surface of the supercage, and stabilize the nickel cation with propene. That's the first stages over here. Then you have the dimerization, but as that's proceeding, you have a competing process, which is a pair of these in the same supercage coming close enough to each other that you form a bridge with an alkene, and that deactivates both nickel cations. So if I can keep just one cation per supercage, the catalyst is active. Now, even more interesting is what's the product distribution. And we've done a very careful analysis of all the isomers of hexene, there are quite a few, but we discovered that 60% of the product is linear, with the internal olefin being preferred. 35% is monobranched, and only a very small fraction, 5%, is dibranched. So that's what you get with nickel exchanged into sodium X. And what we'd like to ask is, are the rates of forming these products and the distribution of these products dependent upon the nature of the cation? And so what we're going to look at here is, in the case of the alkali metals, is going from sodium to lithium and then over to potassium. And then we'll compare catalysts with divalent cations such as magnesium, calcium, or strontium. And we're going to ask, how does this affect both the activity and the selectivity? What we see here is that there's a correlating parameter, which is the free space, free volume inside the supercage. And that as I make that free volume larger, the activity increases. Now the activity, the volume here gets larger as you go from potassium to lithium, because you have a smaller cation, and even though the lattice is getting smaller, tighter, the amount of space available for chemistry inside here is getting larger. There's the nickel cation. Interestingly though, if you go from nickel to magnesium over here, now all these magnesiums are inside the structure of the zeolite. They don't creep into the supercage because they're divalent. You don't need to put them there. And even though you have the same space, you have a less active catalyst. But if you increase the free volume, it increases the activity once again. And this is a consequence of a change in the crystal field. And we're currently doing theoretical studies to understand how the free space and the nature of the crystal field over here affect the activity. There's also an effect on the selectivity, as you can see from the linear to dibranched ratio over here, and there would be a similar plot for the ratio of linear to monobranch products. It goes down as the free space increases. And this is consistent also with what one sees if you go to the so-called SHOP, the shell oligomerization process, which is homogeneous, that you tend to get principally branched products, mono and dibranched, and not linear. Whereas if you use the confinement of the space here of the zeolite, you can force yourself towards the linear products. Let's move on now and look at the second way of increasing molecular weight. And that's to start with the alkenes, add CO and hydrogen at this point, do hydroformylation and then hydrogenation. And the illustration I'm going to give you is going from propene over here to butanol. And why butanol? Because it's a wonderful gasoline additive, blends better than ethanol, has a higher energy density, and avoids other problems. And so what we're going to look for are two heterogeneous catalysts that we can put into this box and to this box, and then see if we can use them together in one reactor. So we have found that there are two heterogeneous catalysts that will work to do the hydroformylation. The first is to take little nickel particles, expose them to CO and hydrogen in the presence of this phosphoxanthose ligand over here. And that will react with rhodium atoms that are corrosively removed from the rhodium particles to make this kind of a structure. And we prove the existence of this structure by both infrared spectroscopy and NMR for the phosphorus over here. The other kind of catalyst you can make is to take sulfoxanthose, this molecule over here, dissolve it in ionic liquid and impregnate silica with that and with a rhodium precursor, and you'll make this active center in situ. So this active center in both cases looks very similar, and not surprisingly, the activity of both these centers are identical, as are the kinetics. So this shows you that you can make a heterogeneous hydroformylation catalyst that is quite active. To do the second step, the hydrogenation, we want to go from the alkanal, in this case butanal, with hydrogen to the butanol. And it turns out that that can be done with what is called Schwab's catalyst, which is shown here. It's a dimer, which under reaction conditions breaks up into two monomers. And they will do the hydrogenation of this aldehyde over here, or alkanal, in the presence of an alkene. So they don't hydrogenate the alkene, but they do hydrogenate the aldehyde. And they treat the the products isobutanol and butanol, the two coming from the two aldehydes, the same exact kinetics. So now you can put these two pieces together. You put the hydroformylation catalyst shown in red here on top, the hydrogenation catalyst below, pass a mixture of propene, hydrogen, and CO, and out of the bottom comes butanol, unreacted CO, and unreacted propene, and all of the hydrogen is consumed along the way. And we're using the two catalysts that I just shown you earlier. And this works quite well. In this example, we can get up to 15% conversion of the propene for the conditions we chose, but approaching 90% of the aldehyde is converted to alcohol. By adjusting the space velocity and the relative magnitudes of the weights of the two catalysts here, we can drive this system all the way to 100% butanol, so 100% conversion of propene to butanol. Let's look quickly then at the last of the three options, which is to do hydroformylation followed by alcohol condensation. Or as I said earlier, you don't have to do hydroformylation. You could produce the alkanal over here by dehydrogenation of an alcohol derived biologically. But in any case, you start with an alkanal. You're going to take off water and make this condensation product, and if you like, then you can hydrogenate that very readily to make branched alkanes, which are liquids. So we took for this catalyst a lesson from biology, knowing that both proline and glycine here, which have a pair of base and acid centers on the same molecule, will do alcohol condensation. And the way we produced the same structure inorganically is to graft an alkylamine, a silicon bonded to carbon alkylamine here with 3 chlorines on it. So these chlorines interact with the hydroxyl groups on silica and give you this structure over here, the tripod, which attaches you to the surface but the main part is this propylamine. And we made both the primary, the secondary, and the tertiary amine to look at their activity. Now, it turns out that both the amine functionality and the hydroxyl functionality are necessary for catalysis, just as in petroleum. Now, I'm showing you here that the most active catalyst by far is the secondary amine. And it has nothing to do with the basicity of the various amines. It doesn't follow the trends in basicity, but it has to do with the fact that you can make an enamine. This word over here, this should be an N, enamine over here, and I'll show you why that's important as you look at the mechanism. The aldehyde comes in, sees a pocket where there are amine groups and hydroxyl groups, interacts with the hydroxyl groups, and we know this because we can see the modification in the stretch of the carbonyl by infrared. Water is lost, so I go down to this structure and I form the enamine, this bond over here, which is then isomerizing and reacting with the second aldehyde, as shown going from here to there, and reacting over here, and then making the dimer at this point. Water is excluded, the product comes off, and it quickly sheds an additional water to give you this alkene, this double bond over here. And this product can then be hydrogenated. So this scheme explains the kinetics that we observe. So what I've shown you in this talk is that you can take Fischer-Tropsch synthesis over cobalt, modify the products by using a small amount of manganese, and it takes the methane yield down, increases the wax yield and C5 plus yield in general, and we're now studying how that happens and why it happens. And you have three options for taking the light alkenes that are derived from Fischer-Tropsch synthesis and turning them into liquid products. The one being oligomerization, the second one being hydroformylation and hydrogenation, and the third being hydroformylation followed by aldol condensation. So with that, I'd like to conclude, thank the individuals who did this work, who are listed here, and thank BP for the support through what is now called the XC Squared program. And Bert, again, congratulations to you, and thanks to the organizers for the opportunity to be here.
Thank you very much. The floor is open for some questions.
Yeah, Richard.
Very interesting, Alex, especially your promoter effects by manganese. This reminds me, and you of course also, of promoter effects of vanadium oxide and other oxides on rhodium.
Mm-hmm.
We studied those, of course, a long time ago, and what we observed on those days was that these promoters would actually bind the carbon atoms much more strongly to the surface than in the absence of the promoters. Now that could explain your reduced methane make.
Right.
That's my question. So do you know anything about the reactivity of carbon on this catalyst?
We don't know that yet. One of the problems is that we want to first identify how the manganese is sitting in contact with the cobalt. There are several ways to think about this. One is if you had little manganese oxide patches and they exposed Lewis acid centers, this would help rupture the CO bond and could explain in principle the higher activity. But the product distribution change that you see looks as if you have dropped the hydrogen to CO ratio on the catalyst without changing it in the gas phase. Now we have some evidence to say that manganese will enhance the CO adsorption. What we don't know is does it also affect or not affect the hydrogen chemisorption? And that's what's in progress right now. Yeah. Huh?
My picture here is that the manganese is now influencing the segregation of the surface. And now you have the little olefins. Normally they are hydrogenated and therefore you cannot incorporate them.
That's correct.
But now, if you inhibit this a little, then you have hydrogenation of the olefins, and then you have no longer this effect of higher compounds from this incorporation. And so in terms of surfaces would mean that you no longer have these hydrogenation sites, which are different from the growth sites, which are common hydrogenation sites, which are probably also good for methylation, and you inhibit this part. Huh? So this is my picture, my view of that.
Yeah, your view is actually quite correct, because if you look at low pressure, what happens, the olefins get hydrogenated because you don't have enough concentration of them to drive them into the chain growth process. And you see the paraffin paraffin proportion of C2 through C4 increasing, and the olefin rapidly decreasing. If you sum the two, they're constant. At high pressure, the alkane proportion is staying nearly constant, but the olefin proportion is falling because you're consuming them for oligomerization. And you're not hydrogenating them because you have enough CO on the surface, you're blocking that process. Yeah, so your picture is quite right. Yeah.
Thank you very much, Alex, for an excellent talk. I'd like to ask you about your formation of higher field using the light olefins.
Yeah.
You have three pathways: oligomerization, the hydroformylation, and the alkyl condensation. Which one you feel is the best pathway in terms of like really for technical for commercial application?
Right. So probably the oligomerization, which is the simplest of the three. And if you can run this at high pressure, which can be done, it's been shown in the patent literature, shown industrial can be done. In fact, your stability goes up because at high pressures of alkenes, these dimers start to break up, the ones that are deactivating the catalyst, and so you can maintain activity for a more extended time. So that's one possibility. We have found that higher olefins also oligomerize quite nicely, particularly butene. Isobutene makes isooctane, which only one product, and that can be made into isooctane. So this is quite viable, I think. But whether X is the best zeolite, I don't know yet. There's a lot of work to be done.
One more question.
To stay with oligomerization, you very clearly showed the big difference in available volume in the supercage, but at the same time you change quite a lot the basicity of your material. Do you take that also into account in justifying the quite impressive improvement in catalytic activity?
Yes, you have as much as a tenfold increase in activity within one series of cations. And we feel that that is largely due to the change in the free volume. So the initial calculations we've done are for sodium and lithium, and they show the right trend. The activation energy for oligomerization with lithium is smaller than it is for sodium. And we think that that's associated with the available free volume. We'll do the potassium one. Then the crystal field effect comes when you compare lithium to magnesium. And that we have yet to do theoretically to see how much the crystal field now is affecting things at the same free volume. So this concept of using free volume is relatively new. We just uncovered this a few months ago. But we see that it plays a role in many zeolitic reactions. Okay.
Well, I would like to mention that Professor Bell will be at the special awards dinner tonight, and if there are any additional questions, I don't want to cut it off here, but we probably want to take the break now and be back at 10:20, and please help me thank again Dr. Bell for this
Catalysis, Professor Holman from the Norwegian University of Science and Technology is awarded the Natural